Today for geometry we're looking at lesson 2.8 on proving angle relationships. In this lesson there are many new postulates and theorems, and I would make sure that I'd have my key concepts packet next to me while I do this lesson, because many of the theorems and postulates come from the lesson, which should be in that packet. Also, from here on out, most everything is going to need either an explanation, proof, property, postulate, or theorem. So the first example we're going to do is if the measure of angle 1 equals 23 and the measure of angle ABC equals 131, find the measure of angle 3. So we're going to look at this right here, and it tells us that angle 1 equals 23 and angle ABC equals 131, which is the whole thing. You can also see that angle 2 is labeled as a right angle. So we know angle 1, we know angle 2, and we know the total. We need to find angle 3. So one of the first postulates that is listed in this lesson, and I'm going to set it up as a 2-column proof. One of the first things that's listed here on page 151 in the book is postulate 2.11, which is the angle addition postulate, which says that if you have 3 angles, 2 added up would equal the total minus the third, or you could just think of it as 2 of the angles added up equals the third. So we have, oh, that doesn't make sense. Sorry, that I didn't mean 3. You have 2 angles, but obviously both of those angles added up equals the total angle. Okay, so this first one, we're given that angle 1 equals 23 and angle ABC equals 131. And like I said, we're going to use the angle addition postulate because we need to find the third angle. So we have angle 1 equals 23 plus angle 2, which was 90, plus angle 3 equals our total, or angle ABC. Then we're going to use the subtraction method. Well, actually we're going to add first. We're going to add angle 1 and angle 2 together to get 113. So then we have this equation. So that's the addition property. Then we're going to have to subtract the 113 to solve this for angle 3. And that's, of course, the subtraction property. And then we are going to be able to solve for angle 3 by doing 131 minus 113, which gives us 18. And I said a lot of times when you've already done all of the operations to write substitution or simplify as your last step. So that's what I'm going to do. So there's your first proof. Next proof we have is angle 6 and angle 7 form a linear pair. If angle 6 equals 3x plus 32, it's going to be here. And angle 7 equals 5x plus 12. We need to find x, and we also need to plug that into angle 6 and angle 7 to find that. So if we set this up as a 2-column proof, we have the givens, which is angle 6 and angle 7 form a linear pair. And angle 6 equals 3x plus 32, and angle 7 equals 5x plus 12. That's going to be our given. Then if you look through the lesson here, you're going to see that we have two new theorems, which are called the supplement and the complement theorem. So that basically says that if you have two angles that form a linear pair, they're going to always be supplementary. And with that same idea, if you have two adjacent angles that form a right angle, the angles are going to be complementary. So we're going to use the supplement theorem to say that angle 6 plus angle 7 equals 180. And then we're going to use substitution to plug in the values for angle 6 and angle 7. Then we're going to have to solve like an equation, so we combine like terms. That's also basically simplifying or substitution. So we get 8x plus 44 equals 180. And we solve the equation by subtracting. I'm going to need some more room here. Let me go here. And then we're going to get 8x equals 136. That's substitution or simplify. And then we divide again to solve. And we get x equals 17, which is the substitution property. And then you're going to have 3x plus 32 that you're going to have to plug in 17. So that's also substitution. And that's going to give you 83. And then you substitute again for the other angle. So you have all three values, and you've done a proof. And then our next example, it says, in the figure, angle ABE and angle DBC are right angles. Prove that angle ABD is congruent to EBC. So we're going to do a proof here, and there's a few other theorems and postulates that we're going to include here, so I'll talk about those as we go. So we're going to set up our two-column proof. We have to prove angle ABE, or not prove, we are given that angle ABE and angle DBC are right angles. And then if we know that a right angle equals 90, so we have numbers to work with, we write them out as equaling 90, and that's going to be the definition of a right angle. And by the picture, oops, too far. By the picture, which is actually, I guess there is not a picture drawn. Oh, here it is. By the picture, you can see that angle ABE are right angles and DBC are right angles, so that would make ABD here and DBE here complementary angles. So we need to tell that ABE and or ABD and EBC are congruent, so that will help us get ABD and EBC related. So we have angle ABD, and I would suggest hopefully you did like a sketch or something so that you have this in front of you at all times, because it gets a little confusing if you don't have the visual. Because we're going to be jumping back and forth. So we said that they're complementary, as well as the other set of angles that equal 90. Let me go to the next page. So angle DBE and EBC are also complementary. And that is a new theorem. That's going to be the complementary theorem, or complement theorem, where if they are added up to equal 90, they're also considered complementary. So, by that same measure, there's one more theorem, and that is the congruent complements theorem and the congruent supplements theorem, which mean that if you have two angles that are complementary to the same angle, or two congruent angles, they are also congruent. That's on page 153. So that's going to be our final step. It's kind of like substitution, but we can also say that these two angles are congruent because of the congruent complements theorem. And I believe there was one more example, excuse me, right here. If angle 3 and angle 4 are vertical angles, so this one doesn't have a picture, but we can we know about vertical angles from previous, like the definition of it, meaning they're congruent. And basically what we can say is the vertical angles theorem says that they are congruent. So it can be proof that it's congruent. So we're going to use that theorem to start, because we want to solve for x to find angle 3 and 4. So we're going to need to know what to do with angle 3 and 4. So we have angle 3 is, excuse me, whoops, angle 3 and angle 4 are vertical. That's our given. And then from there, we're going to use the vertical angles theorem to say that they're equal. And then now we can substitute what the angle 3 and angle 4 are. So that's 6x plus 2 and 8x minus 14. And then we're going to solve. So we need to combine like terms here. You can either use the addition property or the subtraction property or both. So we have 2 equals 2x minus 14. That was subtraction for me. Then we continue to solve. This would be addition now for me. And then we do dividing. To get x equals 8. And that is going to be substitution or simplify. And then we substitute x equals 8 into each angle. To get them. So we have angle 3 is 50 and angle 4 should be congruent, but we're going to substitute and show it anyway. So we have both of them equaling 50, and that concludes lesson 2-8.